Hi, I'm Dave Rich, and I'm a methodology expert with Mentor. I'm going to talk to you about the Verilog basics behind System Verilog constrained random verification. And why is this an important topic? Well, the motivation is we're seeing a lot of people spend more time in debug than any other project task. And that's more than the planning, development, and running tests. And a significant part of that debugging time is spent dealing with constraints. So in my agenda, we're going to cover an overview of constrained random verification for those of you who may be new to this topic. And then we'll go over the Verilog rules for evaluating expressions. High-level view of constrained random verification. What we're doing is defining stimulus at a high level of abstraction. We're creating a random space, and then we're defining constraints or a set of system constraints that define all the possible scenarios that we want to stimulate our design. And this can be more efficient than individual directed tests, but you can of course complement a mixture of this by having random tests and directed tests in your verification process. But anytime you have random constraints and random stimulus, you need an automated way of checking your results, and you need to assess exactly what you've tested, and we call that metric-driven verification. So typically we use functional coverage to figure out what have we actually tested against our plan of verification. So if we look at a sort of a raw example of what a constraint is, here we have two variables, x and y, and the constraint we want to generate to is x less than y. So the brute force way of doing this is randomizing x, then randomizing y, and then seeing if x is less than y. And if it's not true, we'll try it again. And we'll just keep doing this over and over again. This can actually waste a lot of time randomizing and then throwing out the invalid results. Imagine if you had a large set of equations and you may never reach a solution. It could be that your constraints don't have a solution, or it just takes too long. The probability of getting a valid solution is so low that you just may never see it. You can take an approach of creating random variables in a sequential order if you know their dependencies. So if I know that x has a value between 0 and 2, and so whatever I choose for x, I know that y has to be x plus 1 to the value of 3. But this gets very complex when there are more constraints added. So for example, if you had the least significant bit of x is not equal to the least significant bit of y. So this becomes much too difficult. So what a constraint solver does is it takes a set of random variables and a set of constraint expressions and feeds that into a constraint solver. And what the constraint solver does is it figures out a solution space, and it will figure out all the possible combinations, or it will generate a failure saying I can't find any solutions for this. And then once it finds the solution space, it picks a solution, and you can randomize many times, and it's basically what it's doing is picking different solutions out of that solution space. Now the way System Verilog does this is it ties randomization to the object-oriented class system. So we define a class and we declare random variables. So here we have address and data declared as with a rand keyword, and packet number is another class member, but it will not be randomized. Then we add a set of constraints, and for example, two least significant bits of address need to be 0 when I randomize. Then we call the randomize method on this class after constructing it. And the randomize method will return true if it found a solution, and it returns false if it doesn't find a solution. So one thing to remember is that you should always test the result of the randomized method. And there may be a variety of reasons why you might want to do something and change your course of stimulus based on the randomization not succeeding. So let's take a look at that example with the two random variables x and y again. And so we have the constraint x less than y in our class, and we can see that there are 6 possible solutions. Now the solver will go about using some kind of formal technique, which we don't really need to go into here, but whether it actually builds a table or just creates a mathematical model of all the possible solutions, it really doesn't matter. What you just need to know is that there's 6 possible solutions here. The constraint solver will pick the random variables as a set. So it might choose x1, y equals 2. And each solution has an equal probability of being chosen. So out of these 6 solutions, we see that x